Hello everyone and welcome to my video on resonance part 4. In the earlier videos we have discussed about what is resonance, what are canonical structure and resonance hybrid structures. We have learned how to draw them, certain points to remember while drawing them, how many resonance structures are possible for a molecule, ion or radical. We have also discussed about the stability of the resonance structures. Resonance play an important role in chemical reaction. It can control the acidity and basicity of the compound. It can determine the stability of the isomer and also the mode of reaction. In this video, we are going to see that how resonance plays an important role in determining the acidity and basicity of the compound. First, let us see how resonance can be used to determine the acidity of the compound. Phenols are stronger acids than alcohol. Why? It is because of resonance. Phenol, when loses a proton, gives phenoxide ion. Alcohols, when loses a proton, gives an alkoxide ion. But the phenoxide ion can be stabilized by resonance. Phenol also can be stabilized by resonance. But can you see some difference in both the resonance structures of phenoxide and phenol? Yes, in phenoxide, the negative charge is delocalized. But in phenol, the lone pair electron is delocalized. And as a result of which, there is a charge separation in phenol, which is not so in phenoxide ion. And so phenoxide ions are more stable than phenol. In alcohol, the alkoxide ion does not have any such stability. Rather, the alkoxide ion is destabilized by the plus I inductive effect of the R group. And so, alcohols are less acidic than phenol. Carboxylic acid is stronger acid than phenol. Why? This is also because of resonance. Carboxylic acid, when loses a proton, gives a carboxylate ion. This carboxylate ion is more stable than phenoxide ion. Why? Because let's take methanoid ion as an example. In methanoid ion, the negative charge undergoes resonance and we get two resonance hybrid structures in which the negative charge is delocalized between the two electronegative oxygen atom, and both the resonance structures are of similar energy. So these structures, resonance structures, are very stable compared to the phenoxide ion. Methanoic acid or formic acid can also undergo the lone pair electron on the oxygen can also undergo resonance with the carbonyl group. But here there is a charge separation, and this methanoic, the resonance structures of methanoic acid is less stable than the resonance structure of methanoid ion. And so, since methanoid ion is more stable, so methanoic acid quickly gives a proton and goes to methanoate ion. So carboxylic acids are very acidic because of the stability of the carboxylate ion. These are the pK value of methanoic acid, phenol, ethanol, methanol and methane, where we see that methanoic acid is having the lowest pK value, and the lowest pKa value means the more acidity. Lower the pK value, more is the acidity. Resonance can also be used to determine the basicity of the compound. Aniline is a weaker base than ammonia or cyclohexylamine. Why? This is also because of resonance. These are the structures for ammonia, cyclohexylamine and aniline. Now first let's see what is the relationship between pK value and basicity. pKa plus pKb is equal to 14. Therefore, lesser the pK value, more will be the pKb value, as pKa plus pKb is equal to constant, which is equal to 14. Again, more the pKv value, lesser will be the basicity of the compound, or lesser the pKv value, more will be the basicity of the compound. So aniline is having a pK value of 4.62, which is less, and so the pKv value will be more. More the pKb value, lesser will be the basicity. So aniline is less basic than ammonia and cyclohexylamine. If you see the structure of aniline, ammonia and cyclohexylamine, resonance is possible only in aniline. So, the lone pair electron on nitrogen can enter into resonance with the pi electrons of the benzene ring, and since it enters into resonance with the pi electrons of the benzene ring, it is not available on nitrogen. And since lone pairs are not available on nitrogen, obviously it will act as a weaker base compared to that of ammonia and cyclohexylamine. So that is the reason why aniline acts as a weak base. The basicity of the aniline can be decreased by adding a phenyl ring on the nitrogen. Let's see this. Diphenylamine, aniline, is having a pKa value of 4.62, whereas diphenylamine is having a pKa value of 0.8, which is much lower than that of aniline. Lower the pKa value, lesser will be the basicity. So as we go from aniline to diphenylamine, the basicity is decreasing. Introduction of an electron withdrawing group in the ring also decreases the availability of the lone pair electron on aniline, and that also decreases the pKa value. And so the pK value for paranitroaniline is 0.98. Lower the pK value, lesser will be the basicity. But the basicity of aniline can be increased by adding an alkyl group on nitrogen. Alkyl groups have a plus I inductive effect. And because of the plus I inductive effect, the availability of the electrons, the lone pair electrons on nitrogen, increases. And so it can act as a better base. For example, N-dimethyl aniline has a pK value of 5.15, which is higher than the pK value of aniline. Introduction of an electron withdrawing group in the ring at the para position also increases the availability of the lone pair electron on nitrogen, and so we see higher pK value for both para-hydroxyaniline and para-methoxy. And that's all for today. If you like my video, please subscribe, like, share and comment. Before I end, I want to share a thought. Be a persevere like a mountain and disperse your thoughts like fountain. Thank you.